This is Bob McFetrich with Beckwith Electric, and I'd like to thank you for downloading part 2 of our 6th session in our integrated Volt-VAR control presentation. Session 6 deals with coordination without communications. So how can we implement an integrated Volt-VAR control strategy without requiring communications to all the field devices? In part 1 we went through the basic theory, and in part 2 we are going to look at a utility example. So this is a utility that's actually implemented such a feature. So this particular utility is a major investor-owned utility that operates in the southeastern portion of the United States. And they are currently not penalized for any power factor. So power factor was not a overwhelming driver behind funding of this project. They were more concerned with the voltage profile. And in actuality, their primary concern was being able to reduce the voltage profile in order to be able to reduce upwards of 200 to 400 megawatts of load off of their system at any time. So if they were short generation, they wanted to be able to reduce the load as opposed to having to go out and purchase generation or bring on a more expensive peaker plant. So the goal of the whole program for this utility was to be able to dynamically be able to control the load by controlling the voltage. Now, they have a mix of substations. They have some very urban areas which would typically have LTCs. And then they also have a lot of rural areas that would typically have longer feeder circuits and therefore would go with feeder regulation. But even in some of the more urban areas, their typical design now is to go with feeder regulation more so than LTCs. They were using switch capacitor banks, and they wanted to use them as the primary regulating device. So the goal was to have the switch capacitor banks be the primary regulating device for the downline voltage on the feeder circuits. And one of the reasons they wanted to do that is that they found that pole top capacitor banks were much less expensive than line regulators. So they could buy approximately 3 to 4 600 kVAR switch capacitor banks for the same cost as a set of line regulators. And by using the capacitor banks, they can reduce the number of operations on the upstream LTC and therefore reduce the maintenance cycles. With line regulators, as we discussed earlier, you want to coordinate the time delays so the device closest to the source is first to try to correct the voltage. So if the voltage was low on the entire circuit, the LTC would take that operation as opposed to the line regulator. Where with switch capacitor banks, the capacitor banks could react to that voltage before the LTC and thus reduce that operation. They also found that long-term maintenance costs were less with switch capacitor line regulators. Another advantage of going with the switch capacitor bank over the line regulator is not only will the capacitor bank aid in the regulation of the voltage, but we can reduce line losses by providing the VARs that the load needs much closer to the load. And therefore we can increase capacity on the overall system. So they had a lot of distribution substation transformers, 20 MVA up to 40 MVA transformers that were starting to reach 80-90% of their rating. And they were looking at possibly having to upgrade some of these transformers or build new substation and download some of the capacity off of them. But if we can put capacitor banks closer to the load, then that VAR current does not have to flow through the substation transformers, and that frees them up. Since it's an MVA, less VARs means more real power. So it allows them to delay capital costs for upgrading transformers and allows them to get the best utilization of the existing assets by having the capacitors much closer to the load that is requiring capacitive current. So with that in mind, the overall strategy was to set down some design requirements, implement it, and then see what design requirements needed to be tweaked. So the first design requirement is that they did not want to have more than a 2-volt drop across the entire circuit. So in other words, if they looked at any two customer meters anywhere on that circuit, they did not want to see more than a 2-volt difference. So they wanted to have a flat profile across the entire circuit, and their definition of a flat profile was a delta voltage or a change in voltage of no more than 2 volts from the highest customer on the circuit to the lowest customer on the circuit. Their next goal was to, if the substation LTC cannot, and even if it could regulate the voltage, let the capacitor banks regulate the voltage. So we're going to install switch capacitor banks, and we're going to let them be the primary regulating device. So we're not looking at a capacitor bank as a power factor correction device, but as a voltage correction device. And we want to keep the power factor between 0.98 lead and 0.98 lag. We don't mind going leading because we do have these 20 or 40 MVA power transformers in each distribution substation that do have inductive impedance. And if we want to be VAR neutral to the transmission grid, then we need to be slightly leading at the load side of the distribution buses on these transformers so that the additional capacitance can counteract the inductance of these transformers. And it's very beneficial to be VAR neutral to the transmission grid because it's much more expensive to add VARs at the transmission side for voltage support than it is at the distribution level. So, the first thing we needed to do was they needed to determine how to calculate the total amount of capacitance. And they basically used the same formula we covered in the previous session, part 1 of this session, which is to take the total amount of reactive current present at full load on any given circuit and then multiply that by 110%. And that is the total amount of reactive capacitance or VAR that they would need on that particular circuit. Then they would determine the amount of those VARs that needed to be fixed by doing the same calculation but only at the lowest load point. So we're going to start with the highest load point, add 10%, that's the total. Now we're going to look at the lowest load point, and whatever the VAR flow requirements are at that is what we're going to put down for fixed. The would be made up with switched capacitor banks. For the fixed banks, once they calculated, they would typically use 1, no more than 2 per circuit. If they use 1 per circuit, they're going to put it halfway down the line. If they use 2, then they're going to do a 1/3, 2/3. And these fixed banks would normally be left on at all times. You know, some utilities look at a fixed bank as summer, winter. This utility looks at a fixed bank as just that, on at all times. The remaining amount of our flow is going to be made up with switched banks. So, with the switched banks, the total number of banks required is going to be the total amount of capacitance required minus the amount being supplied by the fixed banks. That tells us the total amount of VARs we need, and then we can divide that by the size of the bank to determine the total number of banks that were going to be used. And the switching philosophy would be that the one furthest from the source would be the first to close, because the end goal is to be able to run a lower voltage, and to do that I need to make sure that the lowest voltage is closer to the source than the end, because that's where the majority of the load is. So I want the end of the line to be at a higher voltage than the front end of the circuit, and therefore I want the cap banks correcting the voltage to start at the end of the line and work towards the front of the line. They selected voltage-controlled capacitor banks for a couple reasons. One, they're less expensive than VAR. We don't need to have the line post sensors or the added expense of the control. Number two is, especially in their urban areas, they don't like to have the capacitors mounted on the primary circuits, the main feeds of the circuit, because they're typically run along major intersections and roads and could be both damaged via vandalism or accidents, and also can be an eyesore. So they typically like to tuck them off of taps. And you cannot do that with a VAR control, because then your VAR control would only be monitoring the current and the VAR flow on that tap instead of over the primary main circuit. So with voltage controls, we can place them anywhere we want. Now, if they were using multiple banks, which typically are, they would stagger the phases. So these are going to be single phase monitor, just like an LTC 3-phase operate. So if we're going to have 8 capacitor banks on one circuit, we're going to start with one bank being mounted and attached and monitoring phase A, the next bank monitoring phase B, the next bank C, and then going back to A, so that we try to balance out the number of banks that are looking at each of the 3 phases, just in case there is a little imbalance between the phases. For the bank sizes, they determined that in order to reduce the number of operations on the LTC, which was the primary driver, we would need to limit the effect any given bank had on the voltages seen at the LTC, so that it would not drive the LTC out of band and cause an operation. So their design criteria was to have the secondary voltage changed by no more than 1.5, and in some cases upwards of 2 volts, but definitely no more than 2 volts on any given bank. With that in mind and doing the calculations, it turns out that for them, they have 2 operating voltages, 12 kV and 25 kV. And so for the 12 kV, they're going to fix their bank sizes for switch banks to be 600 kVAR, and for 12 kV, no larger than 1200 kVAR. For 25 kV. So 12 kV will be 600 kVAR banks, 25 kV will be 1200 kVAR banks. Fixed banks may be larger for these voltage levels, but for the switched banks, that's the way we're going to do it. Finally, they really did not want to use line regulators, and the only case that they would is if the line length was so long that to have the capacitor banks regulate the voltage would drive you into a full-time leading power factor, in which case then we're going to put a set of line regulators in between. So as an example of how they would calculate the numbers in that, let's say that their load flow and their historical data shows that this particular circuit requires 500 kVAR at no load, and 2500 kVAR would be 110%. We would take the 500 and make that a 600 kVAR bank, and that would be the fixed bank used. We would subtract 2500 from 600, and that would leave us with approximately 1800 kVAR. And since this is a 25, or assuming this is a 12 kV substation, then we would have 2 banks of 600. 3 banks of 600 to get to our 1800 kVAR. So in this case, if it was a 12 kV, now if it was a 25 kV, then we would have 1 600 and 1 1200 bank. So, with that in mind, we now have the number of banks. And we want to make sure that the settings are done in an appropriate mode. So we've looked at our circuit. We've determined the maximum amount of allowable VARs at no load and at full load. We balanced them out. And now we have to coordinate between the cap banks we're adding with the existing LTC or feeder regulators, and if we have line regulators. So as we discussed in session, or in part number 1 of this session, we're going to use voltage so that everything's sensing the same thing, and we're going to have time delays. So we want the settings such that the only variance is the time delays. We want them to be operating either a regulator raising or a cap bank closing, or a regulator lowering or a cap bank opening at approximately the same voltage levels, but with differing time delays. And we know that the regulators are monitoring individual phases while the cap banks are only monitoring one phase, but we're trying to correct somewhat for that by having the cap banks monitor different phases for each bank. So, we're going to start at the end of the feeder and work back to the substation. The cap bank should be allowed to regulate or operate before the regulators, so therefore we need the cap banks to have the shorter time delays. and we're going to coordinate the cap banks with the first upstream regulating device they encounter, whether that's a line regulator or whether it's all the way back to the feeder regulator or the LTC. We need to have the separate time delays for the open and the close because we want the cap bank furthest from the source, whether it's the line regulator or the LTC or feeder regulator. We want that capacitor bank furthest away to be the shortest close time delay and the longest open time delay. We must make sure that our capacitor control we select has separate time delays for both the close and the open. We're going to use the negative reactance as we discussed in part 1 to supervise the capacitor banks. So if we have too many banks on to correct the voltage and it throws us into a power factor that's leading by more than 0.98, at that time and only at that time do we want the regulator or the LTC to affect the voltage, and we would want them to raise the voltage to induce one or more cap banks to go off. And we were going to use negative X to do that. So, our regulator settings and LTC settings, again, we want the time delays to be longer than the capacitor banks, and we need to coordinate them if we have downline regulators so the regulating device closer to the source has a shorter time delay than the regulating device at the end or further from the source. For the cap controls, exactly the opposite. We want the capacitor banks to have a shorter time delays, and we want them coordinated so the ones in the back are the first to close and the last to open. We want the limits on our capacitor bank to be similar to the band edges on the regulators, and by having the shorter time delays, we expect the capacitor banks to correct the voltages before the regulators or LTCs have the chance to. So this would be how their typical circuits would look. In this case, we have a longer circuit with a line regulator, and these three capacitor banks would be coordinated with this regulator as it's the first regulating device upstream. These capacitors would be coordinated with this, the feeder regulator, because they are the first ones upstream. And this line regulator would be coordinated with the feeder regulator. So that on this circuit, we don't have a feeder or line regulator, only a feeder, and therefore every one of these capacitor banks would be coordinated back to this line regulator. So if we were to start with this the feeder regulator at 90 seconds, we would want this to be 10 to 15 seconds more, so we'd be looking at 100 and 105 seconds for the time delay on the line regulator. This capacitor bank close would be 30 seconds because we want it shortest. This one would be 40, this one would be 50. And on the open side, this one would be 30, this one would be 40, this one would be 50. Likewise, up here, this is a fixed bank, so we're not going to coordinate it at all. This one is going to be a 30 on the close and a 40 on the close. This will be a 30 on the open and a 40 on an open. And that would coordinate. Now in this case, every capacitor bank is coordinating back. So if we start here at 30, because we have so many capacitor banks, instead of going 10 seconds between each, we're probably only going to go 5 seconds. Or what we can do, because we don't have a line regulator here, is we can stretch this time delay out even further. So we could make this time delay 120 seconds, in which case we can make the close on this 30, 40, 50, 60, 70, 80, 90, and we're still going to have the cap banks 30 seconds shorter than the feeder regulator. So if we would set the feeder regulator in this case to 120 second time delay. We'd start with 30 and go up to 90 on the closes, and on the opens it would be 30 down to 90 going the opposite direction. And that is how we would coordinate the system. Now, that worked fine for a while until this utility started to do more with reclosers and sectionalizing switches and trying to impact their SAIDI and their KD numbers by bringing more customers online immediately after a fault. So in that case, if this was our normal configuration, these two capacitor banks time delay would be coordinated with this regulator, this capacitor bank with that regulator, and this regulator with that regulator. But now, do some sectionalizing. We had a fault on this feeder, and we're picking up this portion of the circuit on an additional feeder, now you can see that we have coordination issues, because now these capacitor banks are not coordinating to this regulator, but are actually coordinating back to this regulator. And this regulator, instead of coordinating back to this feeder regulator, is coordinating back to this line regulator, which then is coordinating back to the feeder regulator. So you can see that if we do the distribution automation and the automatic switching of circuits, we are going to have coordination issues with our time delays on both the regulators and the capacitor banks. So, with that in mind, and summarizing part 2 of this series, the utility started this actually with communications. And they found, after doing approximately 100 units with communications, that the communications added no value and increased the cost by over $1,000 per site. So they actually went back and removed communications from all capacitor controls. Now, they do communicate with the substation device, whether it's a feeder regulator or an LTC, because the goal is to be able to go into voltage reduction, and we need to send that voltage reduction command. But that is done only to the regulating device inside the fence. There is no communications with either line regulators or switch capacitor banks. The majority of the circuits are running between 0.96 lag and 0.98 lead, and that is being monitored by the microprocessor-based relays and the feeder or LTC controls in the substation. And they are using the voltage control capacitor banks. They do have the ability now to flatten the voltage profile, and they've actually changed their band centers from 123.5 to 121. So they're basically running in a full-time 2.5 volt reduction mode. But they have the ability to send voltage reduction commands to go even lower than that on a demand need basis. But with that, there were some obstacles. Number one is they are using the negative X to supervise the capacitor bank, so that if you get too far leading, the regulator or LTC will raise the voltage and trip a bank off. The downside to that is when using a negative X, if you have lagging VAR flow, it actually induces the regulator to want to lower the voltage. So if you have a circuit with either too few capacitor banks or capacitor banks that have failed, then you risk having very low voltages at the end of your circuits. So there needs to be a way to coordinate that better with the negative X. Another issue they had is when a cap control failed, it would typically be replaced by a lineman, and the proper time delay settings would not be placed, and then you would have miscoordination. So as the system continued to remain in service, the longer it remained in service, the less benefit they were seeing in the reduction modes, because they weren't having the proper coordination due to controls that were swapped out and not properly set. So the customer, the utility, wanted a means to eliminate this scenario. The final obstacle that they had to overcome was what to do with auto-sectionalizing. One of their new smart grid drivers was to do much more with reclosers and switches, and being able to dynamically switch load either for taking equipment out for periodic maintenance or after faults. And with the voltage controlled and the time delay sequences, all that was hard-coded for one direction, assuming a radial flow. So they wanted the system to still be just as functional and beneficial, even if it was switched in an abnormal condition. So those are the three basic problems that they still wanted to have resolved before they would finalize on this architecture. And in our last part of session 6, we're going to go through some of the new technologies that they implemented in order to accomplish these goals. So I hope that we've enticed you enough to come back and listen to the last part of this 3-part session on implementing integrated Volt-VAR without communicating to the field devices outside the substation. As always, we really value your time. We hope this has been valuable information for you. If you have any questions, you can definitely submit them via our website or contact your regional salesperson or myself. And we hope you have a blessed day. Thank you.